Hello ladies and gents, today we're going to talk about applied functions, variations, section 2.3 in our book. First, they want us to write the expression that expresses the statement. So they give us the statement, x varies directly as z. So when x varies directly as z, that means we're going to come up with the equation x equals kz. So whenever it's directly related, it's going to be x equals some constant k times z. And we can substitute for these variables, a, b, whatever they may use. But when it's directly, it's where we have x equals some constant times z. Right? And this is just some constant, so that means x is just proportionally larger than z, whatever z and x may be. So if they say varies directly, x equals kz or a equals kb, whatever variables they may be using. The next question we have to answer is express the equation as a formula, so just like we did in the first example, but then we need to use the given information to find the constant k. So the expression they want us to write a formula for is z varies inversely as y, so different than the first one. The first one was directly. This one is saying inversely. And then if y equals 2, z equals 10, we need to find the constant k. So first let's come up with the formula, then we'll go through and solve for the constant k. So when they tell us that z varies inversely as y, that means z equals the constant divided by y. Right? So inversely means that whatever variable we are inversely related to is going to be underneath our constant k. So now that we have our equation as a formula, we can now go through and solve for our constant k. So we know that z equals 10 when y equals 2. So we can solve for our constant k by multiplying both sides by 2 to get this off the denominator. And 2 times 10 gives us 20. So our constant k is 20. So we first found our formula, and then we solve for our constant k. And we're always going to represent our constant with a k. Again, we have another where they want us to express the equation as a formula and then use the given information to find the constant. This one again is different because we are using jointly proportional. So that just means there's going to be more than one proportion involved. So before we were using just an x and one other variable, maybe perhaps y, now we have an x, we have an n, and we have an m. So we have two other variables that are proportional to x. So they tell us that x is jointly proportional to n and the square of m. So what that means is x is jointly proportional, meaning n m squared, the square of m, and we're always going to have our constant k. So jointly proportional just means more than one variable is also proportional to our k, or our x here. So first we found our formula, jointly proportional, and then they ask us to find the constant just like in our previous example. So let's plug in what we know. We know that x equals 25. We know that n equals 3. We know that n equals 5. M equals 3. And I should have plugged in a 3 instead. So that gives us a 3 squared, and then we don't know what our k is yet. So let's go through and solve. 25 equals 5 times 3 squared is 9. Okay, and 5 times 9 is 45. So we get k equals 25 over 45. Many times they'll end up with a whole number here, but 25 over 45 works for us too. So here are our 3 examples of directly proportional, inversely proportional, and jointly proportional. So use the information to answer the accompanied example problems on the PowerPoint, and like normal, we'll talk about it tomorrow at the beginning of class.